Damage mechanisms and failure modes in petrochemical services. An academic overview based on API Recommended Practice 571. Definition. A damage mechanism is a specific process that causes degradation of materials or equipment. A failure mode is the observable way that degradation produces loss of function, leakage, rupture, cracking, or wall thinning. API 571 classifies refining damage mechanisms so engineers can link service conditions to the correct inspection and mitigation strategy. API 571 groups damage into four families: mechanical and metallurgical degradation, uniform or localized loss of thickness, high-temperature corrosion, and environment-assisted cracking. Brittle fracture. Definition: a sudden fracture with little or no plastic deformation. Cracks are typically straight and non-branching. The fracture surface is dominated by cleavage. Critical factors include low temperature, thick sections, high stress, and flaws. Prevention uses impact-tested materials, post-weld heat treatment, and control of pressure and temperature versus the minimum safe operating temperature. Inspection alone does not normally mitigate this event-driven mechanism. Creep and stress rupture. Definition: time-dependent deformation under load at elevated temperature, even below yield strength, which can progress to rupture. About a 25-degree Fahrenheit rise, or roughly 15% more stress, can have remaining life. Typical locations: fired heater tubes, reformer pigtails, and dissimilar metal welds. Morphology often shows alligator skin surface fissures. Mechanical fatigue. Definition: cracking from cyclical stress, usually below yield, often causing sudden failure. Cracks start at stress razors, weld toes, notches, and pits. Monitor vibration, pipe movement, and supports. Use penetrant or magnetic particle testing on critical details. Cavitation. Definition: erosion from collapse of vapor bubbles, producing localized impact and metal loss. The key pump factor is inadequate net positive suction head. Appearance: sharp-edged pitting on impellers, casings, and low-pressure piping zones. Carbon dioxide corrosion. Definition: CO2 in water forms carbonic acid, promoting general corrosion in pitting of carbon and low-alloy steels. Critical factors: partial pressure, pH, temperature, and dew point condensation. Mitigate with inhibitors, condensate pH above 6, or stainless upgrades. Flue gas dew point corrosion. Definition: sulfur and chlorine combustion products form acids that condense when metal temperature falls below the acid dew point. Keep economizer and stack metal above dew point, about 280 degrees Fahrenheit for sulfuric acid, and about 130 for hydrochloric acid. Soil corrosion. Definition: deterioration of metals in soil. Critical factors: moisture, resistivity, acidity, and stray currents. Best practice: protective coating plus cathodic protection, monitored by structure to soil potential. Hydrogen-induced cracking forms stepwise internal cracks linking hydrogen blisters, driven by internal hydrogen pressure. Stress-oriented hydrogen-induced cracking aligns near welds under tensile stress. Stress corrosion cracking requires a susceptible alloy, tensile stress, and a specific environment, and typically produces branched cracks. Integrity practice is one loop: identify credible mechanisms, quantify critical factors, set materials and limits, then verify with mechanism-appropriate NDT visual, ultrasonic, radiographic, magnetic particle, and penetrant methods. In summary, the damage mechanism explains how degradation occurs. The failure mode describes how that becomes functional loss. Correct identification using API 571 is the foundation of safe petrochemical fixed equipment integrity.